All right.
I got you.
Okay, that's good. I will try. All right, let's get started. Let me begin with a word of prayer. Ahem. 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 Dear Father, we thank you for this day. Thank you for these students. Just ask you to bless our work today. Help us to just glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. Okay, so I think I forgot to pass the attendance sheet last time, so that means it's a twofer. So you can, if you were here last time, check 126, and then I believe today is the 31st, so, you know, 2 checks. Now, listen, if you don't remember whether or not you were here last Thursday, I can't really help you with that, but do your best. And again, I don't really plan to penalize you for missing class that much. Like, class is its own reward, right? If you don't come to class, then you'll do worse. Like, that's going to happen anyway. So why take off additional points? But I do need to keep a record, mostly because some of you are athletes, and at some point the athletics department will be like, how many times did such and so forth miss class? And I'll be like, Johnny missed 5 classes. Put the screws to him, or whatever, you know, because the coaches they want you to come to class, of course, because the coaches care most about academics. Sports is an afterthought, right? So all right, so listen, I have good news and I have bad news. The bad news is there's no possible way you have enough time to do the quiz in class today. But the good news is I'm giving it to you to work out before next class when we leave today. So relax about the quiz. I'm giving it to you as a homework, all right? And the reason I'm doing that is so we can catch up, all right? Because we're just a little bit behind the plan, and I want to make course. I want to make the class. I need their. You guys got to stop talking, please. I will soon have in my possession an air horn. So, let's see here. You have one with you? You just carry it around? Okay, so listen. So today we're going to talk about quadratic polynomials, equations, you know, the quadratic formula, and graph. All right. So let me start out here with the most basic thing, right? The most basic thing is what we talked about last time, right? Factoring. So if you want to solve a, it's not good. Well, thank you. You'll get your chance, don't worry. So if you want to solve a quadratic equation, why is factoring helpful, right? So let me just proceed by example. Example 1, right? So if we had x squared, minus 3x plus 2, right? And I want to see where is that equal to 0. What's the right way to solve this problem? Well, you factor it, right? Factor it. So factoring gives me x minus 1 times x minus 2, right? And we put that equal to 0. Yeah? And then what? Yeah. Yeah, either that, you're saying either x minus 1 is equal to 0, or x minus 2 is equal to 0, right? The property we're using here is that if we're looking at the product of two real numbers, right, and if their product is 0, it means either one or the other of them, or both, are 0, right? So this is the 0 product property. And as you can see, we get x equals to 1 or x equals to 2. So this is a good way to solve quadratic equations. We can solve quadratic equations if we can factor them, right? We set it equal to 0, and then one or both of the factors must be 0 in order to solve it, right? Let's look at another one, yeah? Example 2. What if we're up against x squared, you know, let's see here. Let me make it more exciting here. Don't look at me. So suppose we're up against 6x squared minus 5x minus 21 equals to 0. All right? Suppose we want to solve that, right? So can you factor it? What would you try? X and X? No, I don't think that.
No, I'm saying like X.
Oh, but so something in here, yeah.
Yeah.
So we need to have whatever we put here. Let's say this and this. Whatever we put here and here has to multiply to 6x squared, right? So yeah, let's try. You say 2x and 3x maybe? I mean, you could whichever, flippity flop, yeah. And 21. How do you get 21? 7 times 3 or 1 times 21, right? Let's probably 3 times 7 looks more. So let's see here. We need a negative 21. So let's try like plus 7 minus 3. Does that work? Because that gives us plus 21, right? Plus 21 minus 6, which is 15. That you know, to quote my community college professor, that dog does not hunt. So we'll get rid of that. So we try something else, yeah? What's next? Which one? I just forgot which I put where. I think let's try putting 3 here and 7 here. See if that works better. How about that? I get plus 9, right? Minus 14. What's 9 minus 14? Negative 5. Oh, and oh, yay, factored. Right? This is the guess and check method. We have to think about the process of multiplying out and factor the numbers that we're creating, right? This 21 is 3 times 7, so that's where the 3 and the 7 came on. Okay, great. Now, how do we solve this? We use the zero product property, like you're about to tell me? Beth Ann?
Yes.
Okay. And so that's 2x plus 3 equal to 0, or 3x minus 7 equals to 0, which gives us 2x is minus 3, or 3x equals to 7. So my solutions are x equals minus 3 halves, or x is equal to 7 thirds. Right? So this is our first and best line of defense for solving a quadratic equation. All right? You factor it and then use the zero product property. This is a very nice way to solve it, right? Are there other ways to solve a quadratic equation? Let's look at some others. So we can also use what's called the square root property. And so I'm going to illustrate this with some examples. So here, my example 3, this will be kind of made to order. Suppose you come across the equation, it's sitting in an alley somewhere, and you're asked to solve it. So you got x minus 2 squared equals to 9. Yeah? So the square root property says the following. It says that you can take the square root of a square. All right? But here's the tricky thing. When you take the square root of both sides, it gives you x minus 2 is equal to plus or minus the square root of 9. Now I'll derive that for you in just a second, but let me just show you how we work this directly. So plus or minus, what's the square root of 9? 3. So 2 plus or minus 3. So we either get x is equal to 5 or minus 1. So this is nice, right? If you have your quadratic equation written as a square equals to a number, these are really easy to solve, right? Let me explain why that's true, yeah? So this equation, right, we can trade for what? X minus 2 squared minus 9 equals to 0, right? And when you do that, this is really, 9 is what? 3 squared, right? So what we're looking at is the difference of squareds. So you've got a squared minus b squared, which as we know is a plus b times a minus b. That's my difference of squares formula. So applying that to the pattern that we have here, we get x minus 2 plus 3 times parentheses x minus 2 minus 3 equal to 0, right? Which then gives us x plus 1 times x minus 5 equals to 0, right? Which then by the zero product property gives us what solutions? Right, either x plus 1 equals to 0 or x minus 5 equals to 0, which of course then gives us back to what we got a minute ago here, right? See that? So the square root property is a shortcut, right? It's a shortcut that means, like, if you can use the square root property, then you can get away from, you know, the trouble of the factoring. But when can you use the square root property? Not always, right? Like, there's some problems that are nice for it. There's some problems that aren't. So let's look at, like, here's some of the recommended homework problems. Let me look at one of these here. So like example 4, this is like section 1.4, number, I'll do even ones. Why should I do even ones for you guys? The odd ones are in the back. That's right. Thank you. So here's a really stupid one. X squared equals to 121. I'll leave that. I'm going to write another one and then put my book down. Section 1.4, number, let's say, oh, I don't know, 32. Let's do that one. That one is 4x plus 1 squared equal to 20. All right, we'll do that one. All right. And then, once we get those under our belt, we will try our hand at number 34. Of section 1.4, and that one is x minus 4 squared equals to minus 5. All right. So you guys tell me, how about the first one, example 4, how should we do that? Yeah? Oh, it's a perfect square. This is 11 squared? Cool, so that means x equal to what? 11? Well, plus or minus 11 is what that means. Because remember, we have to do plus or minus. It's the square root property, so take square root of both sides. We get plus or minus the square root of 121, yeah? Which is equal to plus or minus 11. A quadratic equation usually has 2 distinct answers, all right? There are special ones where there's just one answer, and it's repeated, okay? But usually there are 2 answers. Okay, so how about the next one here? We take the square root property, right? So we have 4x plus 1 is equal to plus or minus the square root of 20. All right, so solve for x. We get 4x is equal to minus 1 plus or minus the square root of 20, which gives me x is minus 1 plus or minus the square root of 20 over 4. So there you go. Those are the 2 solutions to this quadratic equation. So what should we use? Should we use the zero product property or should we use the square root property? The answer is yes, right? Like it depends on how the problem comes to you. Okay? So if it's easy to factor, factor it. Use the zero product property, right? If the problem's already a square, well, wonderful. Use the square root property to solve it. So what's different about example 6? What happens when we use the square root property? X minus 4 is equal to plus or minus the square root of minus 5. What is the square root of minus 5? There can't be one? Well, yeah, but this is the thing, is this is a complex number. So what we get is x is equal to 4 plus or minus the square root of minus 5. So the answer in this case is a complex number. Let me tell you more about that. So what are the complex numbers? Complex numbers, C, is numbers of the form a plus ib, all right? Such that a and b are real numbers, and I is the square root of minus 1. So this is the complex number system. This I is maybe something you haven't thought about much before, but I squared is the square root of minus 1 squared, which is minus 1. So complex numbers are kind of different, right? I mean, like you can't have the square of a real number be a negative number, right? That's impossible. But by construction, complex numbers are a special extended number system where the square of the number is minus 1, in this case, the identity. So like, you know, just for an example, just to give you a quick example here is if I have like the square root of, oh, I don't know, minus 9. The way to do that is just formally, you can think about it like this. That's the square root of minus 1 times the square root of 9. Like that makes sense, actually. And the square root of minus 1 is I. The square root of 9 is what?
3.
So yeah, this is I times 3. Or you could write 3I. So essentially this, if you have the square root of a negative number, you can pull the minus out and convert it to an I. So the square root of like minus a number, all right, is equal to I times the square root of that number. I'm assuming that the number is positive here. You're like, why are you writing hashtag? That is not a hashtag. There are no hashtags in this course. It's a pound. It's a pound symbol. Right? Like pound me too. Let's see here. No, I'm sorry, hashtag me too. This really changes its meaning if you change it to a pound. Let's see here, plus or minus I times the square root of 5 would be this up here. So hashtag. I think the first time I heard hashtag was a student talk about, I don't know, goodness gracious, what was it, 10 years ago now? Like they're giving this talk on some kind of math, and at the end time they're like hashtag Stokes theorem, hashtag blah, blah. I was like, what are they talking about? They thought it was very trendy. I didn't realize it was a harbinger of things to come. Anyway, so the answer here is that complex. So the answer is a pair of complex numbers, all right? Just a little bit more about complex numbers. I don't have much to tell you about complex numbers, guys. But here's another one. So what if you had like 3 plus 2i times 3 minus 2i? What happens here? How do you multiply complex numbers? I feel like I should talk to you guys at least about 5 minutes about complex numbers, because how many of you are comfortable with complex numbers? Like nobody, right? And that's fine. But it is a fact that complex numbers come into the discussion. See, because when we're solving a quadratic equation, some of them have solutions which are complex numbers, right? Some of them don't. How do we decide which ones have the complex solutions and which ones don't? That's a question that we need to ask and answer today, all right? Okay, so multiply this out just for the sake of, how do you multiply complex numbers? Well, FOIL, right, just like regular numbers. So 3 times 3 is 9. And then we get 3 times, well, negative 6i plus 6i minus 4 times I squared, right? So what happens is the imaginary pieces cancel. See that? And you're just left with 9 plus 4, which is 13. Yeah.
So how did you get, I understand what you did there, but how did you get 13 with the I squared?
I squared is, remember I squared is minus 1, right?
Oh, yeah.
By construction, like I squared is minus 1. So what's going on here is this, if we call this number z, then this right here is what's called z bar. So like if you have z is x plus iy, then z conjugate is x minus iy. So this is called the conjugate of z. And what this example is showing you is that if you multiply a complex number by its conjugate, you get a real number again. See that? We had a complex number times another complex number, and we got back a real number. What's the significance of this number? Do you guys know? It's a what? It's a prime number? Oh, nothing like that. Nothing like, good guess, but 13 is prime. That's true. Actually, that is part of a larger story in number theory, the fact that this is a prime number and that it can be derived from the product of these two numbers like that. There's an interesting story to tell there, but one I definitely shouldn't tell here. And so look, if we just do, if this is the x direction and this is the y direction, where is 3 plus 2i? Well, if you do this kind of thing, if you want to plot complex numbers, you plot them in the xy plane. Typically, you make the y-axis the imaginary axis, and you make the x-axis the real axis. So like the number z, 3 plus 2i, is right here, all right? What's the distance of that number from the origin? Like what's this distance right here? So let me draw a triangle here, yeah? See this triangle? The base of it's 3, the height of it's 2. How long is the hypotenuse?
13.
Right, yeah, c is equal to the square root of 13. So the significance here is like whenever you take z times z bar, it's always going to be the distance of z from the origin, and you square it, all right? Listen, I will test you on none of this, so relax. I'm just giving you just a couple minutes on complex numbers just so you have a little bit of introduction to them, all right? All we really need complex numbers in here for are for what we already did in example 6. This is pretty much the end of the road for us. We need complex numbers because they are solutions to quadratic equations, and that's it. All right? So if I ask you to find the solution to the quadratic equation, possibly complex, then you might need to put an I in the answer, okay? On the other hand, if I say find the solution to a quadratic equation, only allow real answers, well then, what would you say in this case? No solution, right? No real solution to this problem. Where'd that come from? It's got a hairball on me. That's different. I've been distracted by fruit flies before. I had that in course evaluations one semester. Professor, very distractible, always getting distracted by fruit flies. Hey, when you teach next to the cat cadaver lab, fruit flies gain a different meaning. Because you don't know where that fruit fly's been, I mean, if you guys ate your lunch off, cats soaked in formaldehyde, I wouldn't want to be around you either. Let's see here. Just saying. Don't do that, though. I think studies have shown it's bad for you. And if studies show something, you have to believe it. All right, so we've got factoring. We've got the square root property. We have this annoying thing that some quadratic equations have real solutions, and some have complex solutions. Now, the complex solutions, they always do come in conjugate pairs. You see this? The one solution was 4 plus I root 5. The other solution was 4 minus I root 5. That always happens. For real polynomials, the solutions, if they're complex, they always come in this conjugate pair. So that, there you have that to look forward to. But the time has come to talk about the quadratic formula. And in order to talk about the quadratic formula, we need to solve a quadratic equation, but not just any equation, an arbitrary one. So we have a not equal to 0, all right? And a, b, and c, real numbers, all right? And we're going to study ax squared plus bx plus c equals to 0. All right? Okay, so the approach here is to, number one, divide by a. All right, so if we divide both sides by a, we get ourselves x squared plus b over a x plus c over a equals to 0. That's my opening move, divide by a. My next move is to do what we did last class, which was complete the square. So this is x plus b over 2a quantity squared, right? And then you've got minus b squared over 2a quantity squared plus c over a is equal to 0. So what I did there was I added and subtracted b squared over 2a quantity squared. Now, there are two different, there's a couple different paths you can go down here. I'm going to use the square root property just because I think it's kind of easiest to see. So I'm going to isolate the square and use the square root property to finish this here. But there's more to say, so I'll just say this is what I'm doing. But so if I add that to the other side, I get b squared over 4a squared, right? Minus c over a. How do you make a common denominator there? Yeah, I've got a 4a squared versus an a. How do I change a to 4a squared? I multiply by what? 4a, right. So we multiply the second fraction by 4a over 4a, and we get b squared minus 4ac divided by 4a squared, right? And so if you want, you could rewrite that as b squared minus 4ac divided by 2a quantity squared, yeah? Okay, so now we use the square root property to solve this thing. So by the square root property, I'll write it up here, we get x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac over 2a quantity squared. All right? And so we can rewrite this simply as x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. And there you go. That is the famous quadratic formula. Yes? There are three cases to think about, right? Can we say, let's talk about those three cases. So, case one, b squared minus 4ac positive. Case two, b squared minus 4ac equals to 0. Case three, b squared minus 4ac less than 0, right? Those are your three cases. If you think about it here. So I don't think today, so far, we haven't run into case two. Okay, like case 2 hasn't happened yet for us today. But we have seen cases 1 and 3 play out, right? So like, for example, case 3 was example 6. And case 1 is like everything else. Everything else up to this point. Let me unwind that for you if you don't mind. So let me, for example 4, right? Revisit. So we have x squared minus 121 equals to 0. So if you look at that, we've got a equals to 1. We've got b equals to what? C equals to what? So what I'm doing right now is I'm going to revisit examples 1 and 6 just to tell you how that relates to this story I'm telling here, this 1, 2, 3 thing, okay? I'm trying to illustrate this comment with those 2 examples. Okay, so like, what's a? A is 1. The coefficient of x squared is 1. What's the coefficient of x? 0. Very good. 0. There is no x, so it's 0. And c? Minus 121, right. So in this context, what is b squared minus 4ac? What's it equal to? You've got 0 squared, right? Minus 4 times 1 times minus 121, right? It's not so important what that number is. I guess it's 484, right? The point is that this is positive. So in the case that it's positive, what happens is you get distinct real roots for the solution, right? This formula gives you a pair of distinct real numbers when that is positive. What's that? I keep calling it that. It's got a name. What is this thing? What is this? This, by definition, this is called the discriminant. Why is it called the discriminant? Because it discriminates what kind of solution you have. The discriminant positive means that you've got a pair of real solutions. The discriminant 0 means you've got a repeated real solution. The discriminant negative means that the solution is a complex conjugate pair. Like if we look at example 6, and see example 6, it's going to take us a little bit of work to see it, right? Because what was our starting point? X minus 4 squared. Yeah? X minus 4 squared equals to minus 5. So if I FOIL this thing out, I've got x squared minus 8x plus 16 equals to minus 5, which if we rewrite this, we've got x squared minus 8x plus 21 equal to 0. All right. So what's A, what's B, what's C in this one? A is 1. B now is interesting. It's minus 8, right? And C is 21. So what's the discriminant? B squared minus 4AC is minus 8 quantity squared minus 4 times 1 times 21, which is what? So that's, yes, 64 minus 84, which is negative 20. Right? That feels wrong. Just a second. I feel like I've done something feels wrong about that. I should have. Oh, it's fine. It's fine. What's the quadratic formula say for example 6? Like, can I erase? Let me erase this here and show you how quadratic formula solves. Now, we can. Okay, so let's let's talk about this. The quadratic formula. Some people just use quadratic formula for everything. This is utter foolishness, okay? To use the quadratic formula for everything, it's just not wise. For a variety of reasons. I hope to convince you today to not use the quadratic formula, actually. You're like, well, why are you showing it to me? Because it's a standard topic and you need to see it. But it is actually almost always the worst way to solve these problems. So like this problem, as it's stated, we solved by the square root property. We found the answer. It's right here. Great, we're done, right? To solve this problem with the square root with the quadratic formula, I first have to do what? I first have to do this algebra, right? I get to this, right? And then the quadratic formula says what? It says x is minus b plus or minus the square root of b squared minus 4ac all divided by 2a, which in this problem, we've got what? B is minus 8. So I have minus a minus 8 plus or minus the square root of, well, the discriminant, right? So, well, we just worked that out. So let me not work that out again, but that worked out to minus 20, yeah? Divided by 2, right? And if you use the quadratic formula, I do expect you to simplify your answer. So that's not a legit final answer. You need to work it out. You need to simplify it. How do you simplify this? Well, you've got 8 over 2, right? Plus or minus 1/2. The square root of minus 20 is really what? It's I times the square root of 20. Very good. But what is the square root of 20? 2 root 5, right? Because the square root of 20 is the square root of 4 times 5, which is the square root of 4 times the square root of 5, which is 2 root 5, as you just told me. So what we really have here is 4 plus or minus 1/2 times I times 2 root 5, right? And so there you go. Finally, 4 plus or minus I root 5. There's the answer. So to use the quadratic formula for this problem, as it's originally stated in example 6, I have to multiply it out. I have to go apply the quadratic formula. I have to simplify the answer like this. And finally, I'm back to where I got to in 3 steps using the square root property. This is the life that you've doomed yourself to if you insist on thinking of things only in terms of the quadratic formula. You mustn't do this. This is the wrong way of thinking of how to solve quadratic equations. Yes, the quadratic formula will solve any quadratic equations, but it is not always, in fact, it's usually not the best tool. When is the quadratic formula a good tool? Well, like in a science or engineering class where you've got like ugly decimal numbers for coefficients, the quadratic formula is a good choice, all right? Okay, so we just used completing the square on an equation, right? To find the formula for the quadratic formula, right? I want to show you now that we really should just complete the square on examples. That's the right way to solve these. That's the, in fact, better way to solve these. All right, let me show you. So any equation, pretty much any equation we can come up against here, quadratic equation, that is, example 7. So let's suppose you want to solve, woo, yowzers, no. Thank you. Here, let me look in your, thank you. Let's look in section 1.4. All right, so it says solve each equation using completing the square. And it says see examples 3 and 4 in the book. I'm almost certain I'm not doing it the way the book is doing it because there's a better way. Well, I don't know, maybe, I'm not gonna look. Fine. Yeah, it's okay. So here we go. Let me try to explain to you what I'm talking about here. We'll start out with a fairly easy one. X squared minus, so the question is what you're asked. If you're asked to factor the quadratic polynomial, right? And that's an important thing. We need to know how to factor quadratic polynomials. Factoring is related to solving the equation, but it's not the same. Yeah? How do you factor an arbitrary quadratic? See, we didn't quite see that here in this derivation, did we? But I'll show you right here. So what we do is we complete the square. So let me just give some instructions here. We want to factor using completing the square, then solve. All right, so that's what we're going to do. And there are two different paths to go down here is why I'm kind of quibbling. Okay, so how do we complete the square? You take what? Half of 10, which is what? 5, but there's a minus, so we do x minus 5, quantity squared, all right? Minus 25, because the square of 5 is 25, and then the 18 is still there, all right? And then, what do I have? Well, I have x minus 5 squared minus 7 equal to 0. All right? How do I factor? How can I factor this quadratic? Square root, right? You got to look at that 7 and say, well, 7 is the square root of 7 squared, right? So really, we're looking at x minus 5 quantity squared minus the square root of 7 squared. So again, we're back to my difference of squares pattern, a squared minus b squared. Always that. Always look for that. And so we can use that, you know, a plus b times a minus b again. So this is x minus 5 plus the square root of 7. X minus 5 minus the square root of 7 equal to 0. Was it something I said? Was it, let's see here. So, I'll try to behave. All right, so we factored it, yeah? It's factored. So now you can use the zero product property to solve it, right? So either x is equal to, so this, if this is 0, or this is equal to 0, right? So we either get x is equal to 5 minus root 7, or we get x is equal to 5 plus root 7. And there you go. Those are your answers. At no point do you see me calculating the discriminant and identifying what a, b, and c are, right? I don't need to. Because if I follow the derivation of the quadratic formula, I don't need to actually use the quadratic formula. Like the derivation of the quadratic formula is completing the square. And for actual numbers, usually it's much safer to actually do this. Now, there is an even easier, so suppose you're asked a separate question, which is just solve it. So let's look at another example, something like, oh, I don't know, x squared plus 8x, I don't know, minus 2. Solve this, all right, just solve it. So notice that this time I have not burdened us with the factoring problem, okay? I'm not asking you to factor it. I'm just asking you to solve it. What's the right way to do this? Still completing the square, but slightly different path. Check this out. So we do x plus 4 squared, right? Because half of 8 is 4. And then to be fair, I have to do what? I have to subtract the square of 4, which is 16, right? So minus 16 minus 2 equal to 0. And now I'm going to go down a different path than the last example, okay? Now I'm going to isolate the square. It's equal to 18. And now I will use the square root property to solve it. Yeah? So x plus 4 is equal to plus or minus the square root of 18. So the solution is, or the solutions are, I should say. I get so much grief from my own children when I write homework problems wrong. Like if I use a proposition or a preposition out of place or something, oh my goodness, I never read the end of it. Or if I misspell something, oh my goodness. So there you go. Yep.
When would you want us to use, like, because the 18
Oh, yeah, I mean, I'm fine with it. I mean, yeah, you could you could rewrite that as -4 plus or minus like 3 root 2. Yeah, sure.
Would you count it wrong?
No, I probably wouldn't count it wrong there. The place I will count it wrong is over here. If you're just using quadratic formula and not simplifying it, that's where I will count it wrong.
Okay.
But,
like,
yeah.
they think you're doing
And when I say I count it wrong, I mean I would take off like 10% credit or something for leaving it like this as opposed to, making it like it should be.
I'm just talking about over here.
Over here, I wouldn't take off points if you left your answer like that. I don't really
like
care.
that.
This is good. This is better, of course, but this is also fine. I wouldn't take points off for the one I boxed. Any questions? So let's see here. All right, so let's look at a word problem.
Oh no.
Oh no, oh yes, yes. You're like, wait a minute. Hey, listen, here are the rules on word problems. Okay? You ever done bowling where you have the things on the side? Bumpers. Like, I think of word problems in that. Oh, Batman, Robin, right?
Yeah.
Okay, so over here. But so I try to kind of think of bumper bowling when I think of word problems in here, in the sense that I'm going to try to just stick to the ones I've assigned you in homework. So, in section 1.4, I assigned you guys something like 50 problems to practice because I believe in practicing these until you're just bored with it. That's the wrong thing to say. That's probably already achieved. So depending, right? That's the wrong. I've been. I mean, until you know exactly what you're going to do before you start doing the problem, right? So however we should label that. In contrast, I have recommended 5 word problems. 5. So make sure you can do these 5. All right. I will do one of them for you right now. A parking lot has a rectangular area of 40,000 yards squared. Area 40,000 square yards. All right? And we're told that the length, all right, is 200 yards more than twice its width. All right? Find the dimensions of the lot. Find the dimensions of the lot. All right, so that's one. So I think I'm just going to do one word problem today. We can do more of future day, all right? But I'm just going to do this one for today. There are 4 other problems. You guys can just, anytime I say start a class, if there are any questions, ideal chance for you to say, hey, could you work the other word problem? And then I'll do it. So we're supposed to find the dimensions of the lot. So how do we do this? Well, let's see here. So let's say that this is the length, right? And let's say this is the width. It doesn't really matter which you label which, but we do need to understand the relation. The length is 200 yards more than twice the width, right? So that means that the length is equal to what? What's the equation that we have from this sentence? There's no w squared, but the twice the width, right? So 2w, and then what? Plus 200, right? And we'll just work in yards. We won't write 200 yards just to, understand that we're using yards as our unit of measure here, right? And then what? What's the area? Right, area, but it's also equal to what? Length times width, right? But the length is what? It's 2w plus 200, right? So we've got 2w plus 200 times w equal to, as you guys just told me, 40,000. And That's why we're talking about this today. What are we looking at? What's this? That's a quadratic equation, right? In the letter W, but a quadratic equation nonetheless. How do we solve this? Well, I first of all erase my annoying. I'm going to just, if you don't mind, I'm going to make myself some space right here. So first thing I'm going to do is I'm just going to rewrite it so it's a little bit prettier. I've got 2w squared plus 200w minus 40,000 equals to 0. I detest having a leading coefficient that's not 1. Like, it just makes everything uglier. So why don't we just divide by 2? Dividing by 2 will make this problem less annoying. So let's do that. What's that give us? Yeah, w squared plus 100w. 20,000, yeah. I'm going to complete the square because, I love completing the square. So this is w plus 50. Square that thing. What's the square of 50? 50 times 50 is what? 2,500. All right, so I have to subtract 2,500. This is completing the square. I still got my 20,000. And so what this gives me is w plus 50 quantity squared is equal to 22,500, which if you tilt your head and squint, you can see that that's 150 squared. So this gives me w plus 50 is equal to plus or minus the square root of 150 squared, also known as plus or minus 150. So the answer is minus 50 plus or minus 150. I'm just messing around. I happen to know that 225 is the square of 15. You should get a calculator, calculate the square root of 22,500, right? Fine, but it works out to 150, okay? So there are two answers here, right? So either we get minus 50 minus 150, which is minus 200, right? Or we get minus 50 plus 150, which is 100. So, all right, so then what? Okay, so we found thus W equals to what? So how about minus 200 for a width? Right, that is not allowed. We call that kind of thing extraneous, right? I always tell my students that if I was to be a rapper, I would call myself extraneous G. And my tagline would be, I'm not even in the solution set. So there we go. This is extraneous. I have no beats, though. All my beats would have to be bought from someone else because I have no rhythm. I can't even clap and sing. Like, it's not in me. I got to pick a one or the other. You know, that music leader or whatever's like, clap and sing. I'm like, nope. You pick one. You don't get both from me. So 100 yards. Don't even get me started on hand motions for little boys. That's just a cruelty. Length is 2w plus 200. So that is apparently 2 times 100 plus 200. So what's that? The length is 400 yards. So typically when we ask for dimensions, dimensions are given length times width. So like the dimensions are, 400 yards by 100 yards. That's how you'd, if you're going to go buy a carpet or something, you'd ask for it like that, right? Dimensions. But no, I don't take off points if you don't write your answer like that. If you have somewhere in this problem, length is equal to, 400 yards, and the width is equal to 100 yards, hooray. Now, if you told me that the length was 100 yards and that the width was 400 yards, I guess we'd have a problem because there is an asymmetry here, right? Because the one is, they're not, there's, but. All right. So there's your word problem for the day, okay? So it wasn't too bad, was it? Not too bad. So my last topic for today, so this is the Machiavellian approach to introducing the quadratic formula and quadratic equations, which is to say I'm doing my evil all at once. So graphs. How do you graph? What do you mean by graphs? What is the graph of y equals to ax squared plus bx plus c? How do you graph this thing? All right. So let me just proceed by a couple of examples, and then I'll tell you some general things, okay? So example, what are we on? Is this example?
9.
That was example 9, yeah. Oh, and I didn't tell you, but this was number 23 in section 1.5. So all of the recommended problems I gave you from section 1.5, they're all odd numbers. So you can check your answer on the word problems and see whether or not you're off base, right? You should try them though. And if you get stuck, come ask me questions. We got time for that in class, of course, right? Okay, so example 10. So let's try to graph y is equal to, I don't know, x squared minus 8x plus 6. Wait a minute, no. Give me a second here. 12. All right, so here's how I would graph this. A couple things. Basically, to graph so first of all, what are you looking for? What does the graph of a quadratic equation look like? Do you guys know? Nobody knows? It looks like a parabola. All right, so it's a parabola that opens up, or it's a parabola that opens down. So like generically speaking, what you're looking for is it either looks like this, or it looks like that. All right, and it could be that where the turning point is called the vertex. All right, so this vertex could be above or below the x-axis. It may or may not cross the x-axis. All right, so if it has places where it crosses the x-axis, those are called x-intercepts, right? This much I can tell you. If we have ax squared plus bx plus c, where's the y-intercept? So like this one, that's where the y-intercept is for this and this, yeah? So y-intercept, and so it's helpful to use what's called function notation, all right? So we're going to say that this is equal to f of x. So that's just a label to remember that this is a formula. F of x is when we take a times x squared plus b times x plus c, all right? This is the formula. F is for formula, if you like, or function. And so the y-intercept is at 0, comma f of 0. This is like generally true for a function. If you want to find the y-intercept of the graph, you just plug 0 into the formula for the function. That tells you where the function's at when x equal to 0. So what happens here? So if I plug 0 into the formula, what do I get? 12. Yeah, so the 0, 12, that's the y-intercept, all right? How about x-intercepts? So think about this. Where are x